Tonight, we're going to confront a question that sounds like it should have a straightforward answer, but absolutely does not. How many galaxies exist in the universe? You might have heard a number before, maybe 200 billion, maybe 2 trillion. But here's what almost nobody tells you. Those numbers aren't counts. Nobody has ever sat down and counted every galaxy. They can't. Because most of the galaxies that exist in the observable universe have never been seen by any telescope ever built. They're too faint, too small, too far away. The number you've heard is partly a measurement and partly a guess, an educated guess built on some of the most extraordinary observations in the history of science, and the real number might be something nobody has even imagined yet. Before we go any further, if you find this kind of deep exploration fascinating, a quick like or subscribe really helps the channel grow. It's a small thing for you, but it makes a huge difference for me. Now, let's begin. Let's start with something you've probably done without even thinking about it. You've looked up at the night sky, maybe on a camping trip, maybe from your backyard, maybe from a rooftop somewhere far from the city. You saw stars, thousands of them scattered across the darkness, some bright, some faint, some clustered together, others sitting alone in vast stretches of black. Maybe you saw the Milky Way, that pale ghostly band of light arching from one horizon to the other, looking almost like a cloud that forgot to move. And in that moment, if you're like most people, you thought something along the lines of, there must be so many stars out there. And you were right, there are. But here's what you almost certainly didn't think. Almost everything you were looking at belongs to a single galaxy. One galaxy, yours, the Milky Way. Every star visible to your naked eye on even the clearest, darkest night is a member of the Milky Way. Every constellation, Orion, the Big Dipper, Scorpius, Cassiopeia, all of them are made of stars inside our galaxy. That river of light stretching across the sky isn't some separate thing out in space. It is our galaxy seen from the inside. You are looking at the disk of the Milky Way edge on from within it. It's like standing inside a vast forest and seeing trees stretching away in every direction until they blur together into a wall of green. That wall of green is the forest. That band of light is the galaxy. And with your naked eye on the best night of your life, from the darkest place on Earth, you can see roughly 4,000 to 5,000 individual stars. That sounds like a lot. But the Milky Way contains somewhere between 100 billion and 400 billion stars. What you see with your naked eye is less than 1/1,000,000th of 1% of the stars in your own galaxy. You're not even scratching the surface. You're seeing an almost immeasurably thin sliver of your own cosmic neighborhood. And beyond that neighborhood, beyond the edge of the Milky Way, stretching in every direction across a volume of space so large that light itself needs billions of years to cross it, there are other galaxies. Many, many other galaxies. The question is, how many? And the answer, as it turns out, is one of the most complicated questions in all of astronomy. Because nobody has ever counted them. Nobody can count them. The number you've heard, whatever it is, whether it's 100 billion or 200 billion or 2 trillion, is not a count. It's an estimate. And that estimate depends on what we can see, what we can infer, and what we assume about the parts of the universe we will never be able to observe. But before we can understand why the number is so hard to pin down, we need to understand something that might surprise you. For most of human history, nobody knew other galaxies existed at all. The idea that there might be other collections of stars out there, separate from our own, was not just unknown, It was unthinkable. For thousands of years, the universe, as far as anyone understood it, was the Earth, the Sun, the Moon, 5 visible planets, and the stars. That was everything. The ancient Greeks developed models of the cosmos that placed Earth at the center with the stars fixed to a crystalline sphere just beyond the planets. This model made intuitive sense. You could look up and see the stars rotating together as a group, never changing their positions relative to each other. They seemed attached to something. A sphere seemed reasonable. This geocentric model, refined and formalized by the astronomer Ptolemy around 150 of the Common Era, dominated Western thinking for over 1,000 years. In this picture, the universe was small, compact, contained. The stars were all roughly the same distance away, just beyond Saturn's orbit. There was no concept of depth in the cosmos, no idea that some stars might be much farther away than others, and absolutely no notion that there might be other structures out there, other galaxies, other collections of billions of stars separated from us by unimaginable distances. Even when the heliocentric model replaced the geocentric one, when Copernicus and later Galileo showed that Earth orbits the Sun rather than the other way around, the basic picture of the universe didn't change all that much. The stars were still assumed to be at roughly the same distance. The Milky Way was still assumed to be everything. The cosmos got bigger, but it didn't get structurally different. There was still just one collection of stars, and we were in it. Now, to be fair, a few thinkers did speculate about something more. In 1755, the philosopher Immanuel Kant proposed an extraordinary idea. He suggested that the Milky Way was a vast rotating disk of stars held together by gravity, and that other fuzzy patches of light visible through telescopes, which astronomers were calling nebulae, might be separate systems of stars far beyond our own. He called them island universes. It was a brilliant insight, and it was almost entirely ignored, because at the time, there was no way to test it. Nobody could measure the distance to these nebulae. Nobody could determine whether they were small clouds of gas inside the Milky Way or enormous collections of stars far outside it. Without distance measurements, the question was unanswerable, and so it remained unanswered for over a century and a half. By the late 1800s, telescopes had become powerful enough to reveal thousands of these nebulae scattered across the sky. Some were clearly clouds of gas, glowing regions where new stars were forming, but others looked different. They had a spiral structure, they were compact, well-defined, and they didn't look like gas clouds at all. They looked like something else entirely. The question of what these spiral nebulae actually were became one of the most important unsolved problems in astronomy. Were they nearby gas clouds within the Milky Way? Or were they distant galaxies, Kant's island universes, separated from us by millions of light years? This debate reached a climax on April 26, 1920, in an event now known as the Great Debate. Two prominent astronomers, Harlow Shapley and Heber Curtis, presented opposing views at the Smithsonian Museum of Natural History in Washington. Shapley argued that the spiral nebulae were relatively small objects within or near the Milky Way. He believed the Milky Way was the entire universe, an enormous system of stars, perhaps 300,000 light years across, that contained everything there was to contain. Curtis disagreed. He argued that the spiral nebulae were independent galaxies far beyond the Milky Way. He believed the Milky Way was just one galaxy among many. Smaller than Shapley thought, perhaps only 30,000 light years across, but part of a much larger universe filled with similar structures, Both men had evidence, both made compelling arguments, and neither could definitively prove his case. The debate ended without resolution. What they needed was a way to measure the distance to one of those spiral nebulae. If a spiral nebula turned out to be millions of light years away, it couldn't possibly be a small cloud inside the Milky Way. It would have to be an enormous, independent system of stars. But measuring distances across millions of light years in the 1920s was extraordinarily difficult. There was no direct way to do it. You can't stretch a tape measure across intergalactic space. You can't bounce a radar signal off something millions of light years away and time how long it takes to return. The signal would take millions of years to get there, and millions more to come back. You need something cleverer. And that cleverness came from a discovery made years earlier by a woman named Henrietta Leavitt. Leavitt was a human computer at the Harvard College Observatory, one of a group of women hired to analyze photographic plates of the night sky. In 1912, she published a remarkable finding. She had been studying a type of star called a Cepheid variable. These are stars that pulsate, brightening and dimming in a regular cycle. What Leavitt discovered was that the period of a Cepheids pulsation, how long it takes to go from bright to dim and back to bright, is directly related to its intrinsic luminosity. How bright it actually is, not how bright it appears from Earth. A Cepheid that pulsates slowly is intrinsically brighter than one that pulsates quickly. This was a breakthrough of the highest order. Because if you know how bright a star actually is, and you can measure how bright it appears to be from Earth, you can calculate how far away it is. Bright things look dimmer when they're farther away. That's basic physics. The relationship between apparent brightness and intrinsic brightness gives you distance. Leavitt had handed astronomers a cosmic ruler. And in 1923 and 1924, Edwin Hubble used that ruler to change everything. Hubble was working with the 100-inch Hooker telescope at Mount Wilson Observatory in California, the most powerful telescope in the world at that time. He trained it on the Great Spiral Nebula in Andromeda, known as M31, in the MESS-EA catalogue, and he found Cepheid variable stars inside it. Using Leavitt's period luminosity relationship, Hubble calculated the distance to Andromeda. His result was staggering. Andromeda was roughly 900,000 light years away. That was far, far beyond the boundaries of the Milky Way by anyone's estimate. The spiral nebula wasn't a gas cloud inside our galaxy. It was an entirely separate galaxy, a vast collection of billions of stars, sitting nearly 1 million light years from us in the depths of intergalactic space. Hubble's measurement had some errors. We now know that Andromeda is actually about 2.5 million light years away, not 900,000. The discrepancy came from the fact that early Cepheid calibrations weren't perfectly accurate, but the essential conclusion was correct. Andromeda was far outside the Milky Way. It was another galaxy. Kant had been right all along. The Milky Way was not the universe. It was one galaxy among what would turn out to be an almost incomprehensibly large number of others. And just like that, the universe got bigger. Not a little bigger. Unimaginably bigger. The cosmos went from being one galaxy, the Milky Way, containing everything, to being a vast expanse of space containing countless galaxies, stretching in every direction as far as telescopes could see. Within a few years of Hubble's discovery, astronomers confirmed that many other spiral nebulae were also distant galaxies. Hubble himself went on to study the distances and motions of dozens of galaxies, leading to his discovery in 1929 that the universe is expanding. Galaxies are moving away from each other. The farther away a galaxy is, the faster it's receding. This discovery, Hubble's law, became one of the foundations of modern cosmology. But for our story tonight, the critical point is this. The moment Hubble proved Andromeda was a separate galaxy, the question of how many galaxies exist became a real scientific question for the first time. Before that moment, the answer was one, just the Milky Way. After that moment, the answer became unknown, and it has stayed unknown ever since. It has been revised, refined, and reconsidered many times over the past century, but it has never been definitively settled. Now, to understand why this number is so hard to pin down, you need to understand something fundamental about how we observe the universe. We don't see the universe as it is right now. We see it as it was in the past. Because light travels at a finite speed, about 300,000 kilometers per second. Everything we observe in space we're seeing as it was when its light left it. The sun, which is about 150 million kilometers away, we see as it was about 8 minutes and 20 seconds ago. That's how long the light takes to travel from the sun to Earth. The nearest star beyond our sun, Proxima Centauri, is about 4.25 light years away. We see it as it was 4.25 years ago. The Andromeda galaxy is about 2.5 million light years away. We see it as it was 2.5 million years ago. When that light began its journey toward us, early human ancestors were just beginning to use primitive stone tools in Africa. The farther away something is, the further back in time we're looking. When we observe galaxies 10 billion light years away, we're seeing them as they were 10 billion years ago, when the universe was only about 3.5 billion years old. We're seeing them in their youth, long before Earth or our sun even existed. This means that the observable universe is not just a volume of space, it's a volume of space-time. We're seeing nearby galaxies as they are relatively recently, and distant galaxies as they were billions of years ago. Every direction we look, we're looking backward in time, and there's a limit. The universe is about 13.8 billion years old. Light from anything farther than a certain distance hasn't had time to reach us yet. This defines the observable universe, the sphere of space from which light has been able to travel to us since the Big Bang. You might expect the observable universe to be about 13.8 billion light years in radius. But it's actually much larger than that because the universe has been expanding the entire time the light has been traveling. A galaxy that emitted light 13 billion years ago has been carried much farther away by the expansion of space during the time that light was in transit. The result is that the observable universe has a radius of about 46.5 billion light years, making it roughly 93 billion light years across. That's the maximum distance from which any signal, any light, any information can ever reach us given the age of the universe and the rate of its expansion. Beyond that boundary, space continues. The universe almost certainly extends far beyond what we can see. But the light from those regions hasn't reached us. It may never reach us. If the universe is infinite, as some models suggest, then the observable universe, vast as it is an infinitely small fraction of the whole. And here's the critical point. When we ask how many galaxies exist, we need to be extremely precise about what we're asking. Are we asking how many galaxies are in the observable universe? That's a question we can try to answer, at least approximately, because we can observe that volume of space and make inferences about what it contains. Are we asking how many galaxies exist in the entire universe, including the parts we can't see? That's a fundamentally different question. If the universe extends far beyond the observable horizon, and most cosmologists believe it does, then the total number of galaxies could be vastly larger than anything in the observable universe. And if the universe is truly infinite, then the number of galaxies is also infinite. But even restricting ourselves to the observable universe, the number is extraordinarily difficult to determine. And the reason comes down to something deceptively simple. We can't see most of them. Think about what it means to count galaxies in the observable universe. You have a sphere of space 93 billion light years across. Inside that sphere are galaxies at every distance, from nearby galaxies just a few million light years away to unimaginably distant galaxies whose light has traveled for over 13 billion years to reach us. Some of these galaxies are large and bright. They contain hundreds of billions of stars, and they shine with the combined light of all those stars across billions of light years of space. These galaxies are relatively easy to detect. A modern telescope pointed in the right direction can pick them up without much difficulty. But many galaxies are not large and bright. Many are small. Many are faint. Many contain only a few million or a few billion stars. Their light is weak. Spread across billions of light years, their signal becomes so faint that it's nearly impossible to distinguish from the background noise of the sky itself. And the farther away a galaxy is, the fainter it appears. A galaxy that would be easily visible at a distance of 100 million light years might be completely undetectable at a distance of 10 billion light years. Its light has been stretched and dimmed by the expansion of space, shifted from visible wavelengths into infrared wavelengths, and spread so thin across the vastness of intergalactic distance that no telescope on Earth or in orbit can pick it up. This means that every time you try to count galaxies, you're only counting the ones your telescope can see. And the ones your telescope can see depend on how powerful the telescope is, how long it stares at one patch of sky, what wavelengths of light it's sensitive to, and how well it can distinguish faint galaxies from the noise in the image. Change any of those parameters and you get a different count. A more powerful telescope sees more galaxies. A longer exposure reveals fainter ones. A different wavelength reveals ones that were invisible before. The count is not a fixed number, it's a function of your instrument. This is the heart of the problem. The number of galaxies in the observable universe is not something you can simply go out and measure the way you'd measure the height of a building or the temperature of a room. It's partly a counting problem and partly an inference problem. You count what you can see and then you estimate how much you're missing. Imagine you're standing in a vast field on a foggy night. You can see a few hundred fireflies glowing in the air around you. Close ones are bright and easy to spot. Farther ones are dimmer. And beyond a certain distance, the fog obscures everything. You can't see any fireflies beyond that point. But you know they're out there. You can infer their existence from patterns. Maybe the density of fireflies seems constant in every direction you can observe. Maybe the ones near the edge of your vision are clustered in the same way as the ones nearby. Based on these patterns, you can estimate the total number of fireflies in the field, including the ones hidden by the fog. But your estimate depends on your assumptions. Do fireflies spread evenly across the field? Or are they clustered in some places and absent in others? Does the density change at different distances? Are there fireflies beyond the fog that are somehow different from the ones you can see? Your answer depends on your model. and different models give different answers. This is essentially what astronomers do when they estimate the number of galaxies. They observe what they can, they note the patterns, and they build models to account for what they can't see. The result is an estimate, not a measurement. An informed estimate, built on extraordinary observations and sophisticated mathematics, but still an estimate. And it's an estimate that has changed dramatically over time as telescopes have gotten better and observations have gone deeper. There is also a subtler problem that most people never think about. What counts as a galaxy? This sounds like it should be obvious, but it's not. A galaxy is generally defined as a gravitationally bound system of stars, gas, dust, and dark matter. The Milky Way is a galaxy. Andromeda is a galaxy. The large and small Magellanic clouds orbiting the Milky Way are galaxies. But what about a tiny clump of a few thousand stars held together loosely by gravity? Is that a galaxy? What about a diffuse cloud of stars so spread out that it barely holds together? What about a galaxy that's in the process of being torn apart by the gravity of a larger neighbor? Does it still count? Astronomers have definitions, but those definitions have fuzzy edges. The line between a very small galaxy and a very large star cluster is not always clear. Ultra-faint dwarf galaxies, discovered in increasing numbers over the past couple of decades, contain only a few hundred or a few thousand stars. Some of them are so sparse that you could be inside one and not even notice. They're held together not by the gravity of their stars, which is minimal, but by the dark matter halo that surrounds them. Without the dark matter, the stars would drift apart. These objects blur the line between galaxy and not galaxy, and how you define the boundary affects the count. If you set a strict minimum, requiring a galaxy to contain at least a certain number of stars or a certain amount of mass, then you get a lower number. If you use a looser definition, including every tiny clump of stars bound by dark matter, the number goes up. The number of galaxies in the universe is not just a question about what's out there. It's also a question about what we mean by the word galaxy. So where does all of this leave us? When Hubble first proved that Andromeda was a separate galaxy in 1924, astronomers knew of only a handful of galaxies beyond the Milky Way. Within a few decades, telescopes had revealed thousands, then tens of thousands. By the mid-20th century, astronomers were beginning to understand that the universe contained enormous numbers of galaxies, stretching in every direction to the limits of observation. But the actual number remained uncertain. Early estimates in the second half of the 20th century suggested perhaps 10 billion galaxies in the observable universe. Later estimates pushed it higher. By the 1990s, the commonly cited figure was somewhere around 100 billion to 200 billion galaxies. These estimates were based on the best surveys available at the time, extrapolated to cover the entire sky, but even those numbers turned out to be too low. Because astronomers were about to do something that would change the count forever. They were about to stare at an apparently empty patch of sky for 10 straight days and discover that the darkness was full of galaxies. More galaxies than anyone had imagined. Galaxies so faint and so distant that they had been invisible every previous observation. And that discovery would reshape our understanding of just how crowded the universe really is. In the early 1990s, the Hubble Space Telescope was in orbit around Earth, circling the planet every 97 minutes at an altitude of about 540 kilometers. It was, and remains, one of the most important scientific instruments ever built, Hubble sits above Earth's atmosphere, which means it doesn't have to look through the turbulent blanket of air that blurs the view of every ground-based telescope. From its perch in low Earth orbit, Hubble can see the universe with a clarity that no observatory on the ground can match. And in 1995, the director of the Space Telescope Science Institute, a man named Robert Williams, decided to do something bold with it. Something that many of his colleagues thought was a waste of precious telescope time. He wanted to point Hubble at nothing. Not at a star, not at a galaxy, not at a nebula or a cluster or any known object of interest. He wanted to aim the most powerful space telescope ever built at one of the emptiest, most boring patches of sky anyone could find. A spot in the constellation Ursa Major where there was essentially nothing visible. No bright stars, no known galaxies, no interesting features of any kind, just blackness. And he wanted to keep Hubble pointed at that blackness for 10 consecutive days. This was controversial, to put it mildly. Hubble telescope time is extraordinarily valuable. Astronomers from around the world compete fiercely for the chance to use it. There are always more proposals than there is time available. Every hour spent on one observation is an hour not spent on another. And Williams was proposing to spend 10 days, roughly 342 orbits, staring at what appeared to be empty sky. Many astronomers thought it was reckless. Some thought it was career suicide. The fear was that the images would come back showing exactly what everyone expected. Nothing. Empty sky. A waste of time that could have been spent studying objects we already knew were interesting. But Williams had a hunch. He believed that if you stared long enough at one tiny patch of sky, if you collected photons for long enough, faint objects that were too dim to see in any shorter exposure would slowly reveal themselves. He believed the darkness wasn't really empty. It was just too far away and too faint for us to see without an extraordinarily deep look. As director of the Institute, Williams had the authority to allocate a certain amount of discretionary time on the telescope. He used that authority to approve his own project. And between December 18th and December 28th, 1995, Hubble stared at that empty patch of sky, collecting light for over 100 hours across 342 consecutive orbits. The patch of sky Hubble was looking at was tiny, extraordinarily tiny. It covered an area of about 5.3 square arc minutes. To understand how small that is, imagine holding a tennis ball at arm's length. The area of sky covered by that tennis ball is vastly larger than the area Hubble was observing. Now imagine holding a grain of sand at arm's length instead. The patch of sky behind that grain of sand, that speck of darkness barely visible past the tip of your finger, that's roughly the area Hubble was photographing. A tiny, insignificant sliver of the total sky. A patch so small that if you divided the entire sky into equal pieces of this size, you would need roughly 12.5 million of them to cover everything. When the images came back and were processed, what they showed stunned the astronomical community. That tiny, apparently empty patch of sky was not empty at all. It was full of galaxies, roughly 3,000 of them, packed into that minuscule area. Galaxies of every shape and size and color. Some were clearly spirals, their arms stretching gracefully across the image. Some were ellipticals, smooth and featureless blobs of light. Some were irregular, chaotic, distorted, clearly in the process of colliding with other galaxies or being torn apart by gravitational interactions. Some were relatively nearby, their details sharp and clear. Others were incredibly distant, appearing as tiny smudges of reddish light, their images stretched and dimmed by billions of years of travel through expanding space. These faintest, reddest galaxies were among the most distant objects ever observed. Their light had been traveling for more than 10 billion years. When that light left those galaxies, the universe was young. Earth didn't exist. The sun hadn't formed. The atoms that would eventually become you were still scattered across interstellar space, inside stars that hadn't yet exploded. The image was named the Hubble Deep Field, and it became one of the most important photographs in the history of science. Not because it showed anything that astronomers hadn't theorized might be there, but because it proved it. The darkness was full. Every direction you looked, no matter how empty the sky appeared, there were galaxies hidden in the blackness, waiting to be revealed by an instrument patient enough to collect their faint light. But there was a lingering question. Was this one patch of sky representative? Maybe the Hubble Deep Field had been unusually rich in galaxies by some cosmic accident. Maybe that particular spot happened to sit along a filament of the cosmic web, where galaxies were more densely packed than average. If so, then extrapolating from that one tiny patch to the entire sky would give a misleadingly high number. Astronomers needed to check. They needed to point Hubble at a completely different part of the sky and see if the result was the same. In 1998, they did exactly that. A team led by Williams pointed Hubble at a patch of sky in the southern constellation Tucana, about as far from the original deep field as you could get on the sky. This second observation, called the Hubble Deep Field South, was designed to be a direct test. Same telescope, same exposure time, same technique, different patch of sky. If the universe is statistically the same in every direction as the cosmological principle predicts, then the Deep Field South should contain roughly the same number of galaxies as the original. And it did. The Hubble Deep Field South revealed approximately the same density of galaxies as the northern field. The numbers were consistent. The universe looked the same in both directions. This was a critical validation. It meant the original deep field wasn't a fluke. It wasn't an unusually dense patch. It was typical. Any comparably sized patch of sky anywhere on the celestial sphere would show the same thing if you stared at it long enough. The darkness was uniformly full. This confirmation was what gave astronomers the confidence to extrapolate from these tiny patches to the entire sky. If the galaxy density is the same everywhere, then what you find in one grain of sand size patch applies to all 12.5 million equivalent patches. The math becomes straightforward. Multiply the number of galaxies in your observed patch by the number of patches needed to tile the sky, and you have a rough total. And here is where the math gets extraordinary. If one tiny patch of sky, 1/12.5 millionth of the total sky, contained roughly 3,000 galaxies, then you can multiply. Multiply 3,000 by 12.5 million, and you get a rough estimate of how many galaxies might be in the entire sky at the same depth. The answer came out to somewhere around 40 billion to 50 billion galaxies. But that was just the beginning. The Hubble Deep Field, as deep as it was, still couldn't see everything. It still had a sensitivity limit. Galaxies fainter than a certain brightness were still invisible even after 10 days of exposure. There were certainly more galaxies hiding below the detection threshold. When astronomers accounted for this, adjusting the estimate upward to include galaxies too faint for even the deep field to reveal, the number climbed higher. Initial extrapolations suggested roughly 100 billion to 200 billion galaxies in the observable universe. That became the standard figure for years. But the deep fields did more than just count galaxies. They revealed something profound about how galaxies change over cosmic time. When astronomers carefully analyzed the galaxies at different distances in the deep field images, they noticed a striking pattern. Nearby galaxies, the ones whose light had traveled only a few billion years, look familiar. They were well-organized spirals and smooth ellipticals, the same types of galaxies astronomers had been studying for decades. But the distant galaxies, the ones whose light had been traveling for 8 or 10 or 12 billion years, looked completely different. They were smaller, more irregular, more chaotic. Many of them had no recognizable structure at all. They were just clumps. Knots of young blue stars tangled together in shapes that didn't fit neatly into any category. And many of them appeared to be crashing into each other. Galaxy collisions, which are relatively rare in the nearby universe, were extraordinarily common in the distant past. The deep field images showed galaxies in every stage of collision. Pairs approaching each other with their shapes beginning to distort. Galaxies in the middle of a merger, their stars ripped into long tidal tails streaming across thousands of light years. And the battered remnants of collisions that had already occurred. Irregular blobs of stars slowly settling into new configurations. This was direct visual evidence that the universe evolves. Galaxies aren't static. They change over billions of years. They collide and merge. Small ones combine into larger ones. Chaotic, irregular structures gradually settle into the organized spirals and ellipticals we see nearby. The distant universe was a wilder, messier place than the local universe. More galaxies, but smaller ones, packed more closely together, crashing into each other more frequently. This observation would become central to the story of galaxy counting, because it meant the number of galaxies in the universe is not a fixed quantity. It changes over time. The early universe contained far more galaxies than the universe does today, because mergers have been steadily reducing the total count for billions of years. But astronomers didn't stop there. The Hubble Deep Field had shown what was possible. Now they wanted to go deeper. In 2003 and 2004, Hubble conducted an even more ambitious observation. This time, the telescope pointed at a patch of sky in the constellation Fornax in the southern sky and stared for a total of about 11.5 days spread across 400 orbits. The instrument used was the Advanced Camera for Surveys, which was significantly more sensitive than the camera that had taken the original Deep Field. The result was the Hubble Ultra Deep Field, and it was breathtaking. The image revealed roughly 10,000 galaxies in a patch of sky, even smaller than the original Deep Field, covering about 11 square arc minutes. These galaxies were fainter and more distant than the ones in the original image. Some of them had emitted their light when the universe was only about 400 to 800 million years old, less than 6% of its current age. We were looking at some of the earliest galaxies that ever formed. Tiny, irregular clumps of young stars blazing with ultraviolet light. Their images reddened and dimmed by 13 billion years of cosmic expansion. The ultra-deep field pushed the estimate of total galaxies higher. If 10,000 galaxies were visible in that slightly larger but much deeper patch, and if you extrapolated across the entire sky and accounted for the galaxies still too faint to see, the total rose toward 200 billion. Some estimates reached higher. The range was broad because the extrapolation depended on assumptions about how many faint galaxies existed below the detection limit, and those assumptions were uncertain. Then, in 2012, astronomers combined data from the Ultra Deep Field with additional observations taken at infrared wavelengths using Hubble's Wide Field Camera 3. The resulting image was called the Hubble Extreme Deep Field, and it was the deepest image of the universe ever taken. It contained about 5,500 galaxies in a patch of sky that was a subset of the Ultra Deep Field, covering just a few square arc minutes. Some of the galaxies in this image were so faint that they were only barely above the noise level of the detector. They appeared as tiny red smudges, just a few pixels across, their light stretched by the expansion of the universe from ultraviolet all the way into the near infrared. These were galaxies as they existed when the universe was less than 500 million years old, so young that the first generation of stars had barely begun to die. Each of these progressively deeper images followed the same pattern. The deeper you looked, the more galaxies you found. This is an incredibly important point, and it's worth pausing to really understand what it means. The number of galaxies you see is not a fixed quantity, it is a function of how deep you look. If you take a short exposure of a patch of sky, you see only the brightest nearby galaxies. Take a longer exposure and fainter, more distant galaxies begin to appear. Take an even longer exposure and still more appear. Every time you push deeper, you find more galaxies that were below your previous detection threshold. The universe doesn't run out of galaxies at any depth we've reached so far. Every time we've built a better instrument, every time we've stared longer at a darker patch, we've found more. The galaxy count keeps climbing. Now let me explain the extrapolation process in more detail, because understanding how astronomers go from a tiny patch of sky to a total number is crucial, and it's more subtle than it might first appear. When astronomers take a deep image of a small patch of sky and count the galaxies in it, they measure what's called the number density of galaxies as a function of brightness. They ask the question, how many galaxies per square arc minute of sky are there at each level of brightness? The brightest galaxies are rare but easy to see. The faintest galaxies are extremely numerous but hard to detect. When you plot this relationship, you get a curve that rises steeply as you go to fainter brightness levels. There are always more faint galaxies than bright ones, many more. This curve is the foundation of the extrapolation. If you know how many galaxies there are per square arc minute at every brightness level your telescope can detect, you can multiply by the total number of square arc minutes in the entire sky to estimate the total number of galaxies brighter than your detection limit. The full sky covers roughly 149 million square arc minutes. So if you find, say, 70 galaxies per square arc minute down to a certain faintness threshold, you multiply 70 by 149 million and get about 10 billion visible galaxies at that depth. But the curve keeps rising at fainter levels. If you could go deeper, you'd find more, much more. And this is where the estimation becomes tricky. Astronomers use the shape of the curve they've measured, the observed relationship between galaxy counts and brightness, and they extrapolate it downward to fainter levels they can't yet detect. They're essentially saying, if the trend we see continues to fainter galaxies, how many more galaxies are there that we're missing? This requires assumptions. You have to assume the curve continues in a predictable way. You have to assume that galaxies below your detection limit follow the same statistical patterns as the ones you can see. And you have to account for the fact that very faint galaxies may have different properties than brighter ones. They may be smaller, older, or differently distributed in space. Any of these factors can affect the extrapolation. The result is always a range of estimates, rather than a single number. Depending on the assumptions you make about how the faint end of the galaxy population behaves, you get different totals. Conservative assumptions give lower numbers. Aggressive assumptions give higher ones. And the uncertainty can be large, sometimes a factor of 2 or more. There's another complication that makes galaxy counting even harder. It is called surface brightness, and it is one of the most subtle and important limits in observational astronomy. A galaxy's surface brightness is a measure of how much light it emits per unit area of sky. A galaxy can be intrinsically bright, containing many stars, but if those stars are spread out over a very large area, the surface brightness can be low. Think of it this way. Imagine you have a flashlight and you shine it at a wall from a foot away. You get a bright, concentrated circle of light. Now back up to 50 feet and shine the same flashlight. The light is now spread over a much larger area and appears much dimmer. The flashlight hasn't changed. The total amount of light is the same, but the brightness per unit area has dropped dramatically. Galaxies work the same way. A compact galaxy with its stars packed tightly together will have a high surface brightness and be relatively easy to detect. A diffuse galaxy with its stars spread out over a large area will have a low surface brightness and can be extremely difficult to see. It might blend into the background noise of the sky, invisible not because it's too far away, but because it's too spread out. This matters enormously for galaxy counts. There is an entire population of galaxies called low surface brightness galaxies that are very difficult to detect. These galaxies contain plenty of stars, but are so diffuse that they're hard to see against the natural brightness of the sky, even from space. The sky is never completely dark. There's always a faint glow from zodiacal light, from distant unresolved stars, from the cosmic infrared background. A galaxy with a surface brightness comparable to this background glow becomes essentially invisible. It's there, but you can't distinguish it from the noise. The first giant low-surface brightness galaxy discovered was Mollin 1, found in 1987. It turned out to be an enormous spiral galaxy, over 600,000 light-years across, much larger than the Milky Way, but it was so faint that it had been missed by every previous survey. Its stars were spread out over such a large area that the galaxy barely registered above the background. Since then, astronomers have found many more low-surface brightness galaxies, and there are certainly many more we haven't found yet. Every deep survey misses some fraction of these objects because they fall below the surface brightness detection limit, and there's no easy way to know how many you're missing. This means that galaxy counts based on deep field observations are systematically incomplete. They detect compact, high surface brightness galaxies efficiently, but they miss an unknown fraction of diffuse, low surface brightness galaxies. The true number of galaxies in any given volume of space is always higher than what any survey reports, because there are always galaxies hiding below the surface brightness threshold. There's yet another layer of complexity. As you look deeper into space, you're also looking further back in time, and galaxies in the distant past were different from galaxies today. The universe has been evolving for 13.8 billion years, and galaxies have been changing the entire time. In the early universe, galaxies were smaller, less organized, and more numerous. Many of the galaxies that existed billions of years ago have since merged with other galaxies. Two small galaxies collide and combine to form one larger galaxy. The total number of galaxies decreases with time as mergers reduce the count. This means the number of galaxies in the observable universe is not constant. It changes depending on what epoch you're asking about. Right now, today, the observable universe contains fewer galaxies than it did 8 or 10 billion years ago, because billions of mergers have combined smaller galaxies into larger ones. When you look at a deep field image and count the galaxies, you're counting galaxies at every epoch simultaneously. The nearby galaxies in the image are galaxies as they are today. The distant galaxies are galaxies as they were billions of years ago. You're mixing together snapshots from different eras. To get a meaningful total, you have to account for this. You have to understand how galaxy populations evolve with time, how the merger rate changes, how the number density of galaxies at each brightness level shifts as the universe ages. This is enormously complicated. It requires detailed theoretical models of galaxy formation and evolution, informed by observations at many different wavelengths and many different distances. Different models give different predictions, and the predictions are sensitive to assumptions about things like the rate of galaxy mergers, the rate at which galaxies form new stars, and the properties of dark matter halos that host galaxies. Let me also explain what it means when astronomers talk about the redshift of distant galaxies, because this concept is essential to understanding deep field observations. When a galaxy is very far away, the expansion of space stretches the light, traveling from that galaxy toward us. This stretching shifts the light toward longer wavelengths. Visible light gets shifted toward the red end of the spectrum. Ultraviolet light gets shifted into the visible or even infrared range. The amount of stretching, called the redshift, tells you how much the universe has expanded since the light was emitted, which in turn tells you approximately how far away the galaxy is and how long ago its light was emitted. A galaxy with a redshift of 1 emitted its light when the universe was roughly half its current size. A galaxy with a redshift of 6 emitted its light when the universe was only about 1/7 its current size, less than a billion years after the Big Bang. The most distant galaxies detected in the Hubble Deep Fields have redshifts of 8 or higher, meaning we're seeing them as they were when the universe was only a few 100 million years old. At these extreme distances and redshifts, the light from galaxies has been shifted so far toward the red that it moves completely out of the visible spectrum and into the infrared. A galaxy that emits most of its light in ultraviolet, as many young galaxies do because they're full of hot young stars, will appear at infrared wavelengths when observed at a redshift of 6 or more. This is why infrared observations are critical for studying the most distant galaxies. Hubble's infrared camera, the Wide Field Camera 3, was essential for the extreme deep field because it could detect galaxies whose light had been shifted entirely out of the visible range, but even Hubble's infrared capabilities have limits. Beyond a certain redshift, galaxies become too faint for even Hubble to see, regardless of how long it stares. This is why the James Webb Space Telescope, launched in December 2021, was so eagerly anticipated. Webb is optimized for infrared observations. Its mirror is much larger than Hubble's, giving it far greater light gathering power, and it operates at extremely cold temperatures, reducing the infrared noise that can mask faint signals. Webb can see galaxies that are completely invisible to Hubble, because their light has been shifted so far into the infrared that only a purpose-built infrared telescope can detect them, and Webb has already begun to reveal surprises. In its first year of operations, it detected galaxies at redshifts higher than 13, seeing objects that existed when the universe was only about 300 million years old. Some of these galaxies are more massive and more luminous than anyone expected. Theoretical models have predicted that galaxies in the very early universe should be small and dim, still in the early stages of assembly. But Webb is finding galaxies that appear surprisingly mature, with large numbers of stars already in place. This is forcing astronomers to rethink their models of how quickly galaxies can form and grow. These findings directly affect galaxy counts. If the early universe contained more massive galaxies than expected, then the total number of galaxies at high redshifts might be different from what models predicted. And if the models are wrong about early galaxies, they might also be wrong about the total count. So where did things stand after the Deep Field era? By the time all the Hubble Deep Fields had been analysed and the extrapolations had been done, the commonly accepted estimate was that the observable universe contained somewhere between 100 billion and 200 billion galaxies. This number was cited in textbooks, in popular science books, in documentaries, and in countless articles. It became the standard answer to the question of how many galaxies exist. But even as this number became conventional wisdom, some astronomers suspected it was too low. The deep fields, extraordinary as they were, still only sampled tiny patches of the sky. The extrapolation to the full sky was based on assumptions about uniformity, assumptions that the deep field south had helped confirm, but that still carried uncertainty at the faintest levels. If galaxies are distributed roughly evenly across the universe at large scales, which observations strongly suggest they are, then what you see in one patch should be representative of what you'd see in any other patch. This assumption seems solid, but the faint end of the galaxy population, the vast numbers of tiny, dim galaxies that are hardest to detect, remained deeply uncertain. The deep fields told us something revolutionary. They told us the universe is packed with galaxies far beyond what the naked eye or even a casual telescopic glance would suggest. They showed us that the darkness between the stars is an illusion of distance. The darkness is full. Every patch of sky, no matter how empty it appears, contains galaxies if you look hard enough. But the deep fields also had limits. They could only see galaxies above a certain brightness threshold. Below that threshold, an unknown number of galaxies remained hidden. And in 2016, a team of astronomers would try to account for those hidden galaxies. They would look at the problem not just from the perspective of what we can see, but from the perspective of what we can infer. And their answer would be shocking. They would conclude that the 100 to 200 billion figure was not just a little low, it was off by a factor of 10. The real number, they argued, was closer to 2 trillion. And most of those galaxies had never been seen by any telescope ever built. The darkness wasn't just full, it was overflowing. And we had been dramatically underestimating just how crowded the observable universe really is. For decades, the commonly accepted estimate was that the observable universe contained somewhere between 100 billion and 200 billion galaxies. That number appeared in textbooks, in documentaries, on classroom posters, and in virtually every popular science article about the cosmos. It was treated as settled, as close to a final answer as you could get for such an enormous question. And it was wrong. Not slightly wrong, not off by a small margin. It was wrong by roughly a factor of 10. In 2016, a team of astronomers led by Christopher Conselius at the University of Nottingham in England published a paper in the Astrophysical Journal that sent a shockwave through the astronomical community. Their conclusion was startling. The observable universe doesn't contain 200 billion galaxies. It contains roughly 2 trillion. 2 trillion. That's 2,000 billion. 10 times the previous estimate. And the reason no one had realized this before is that most of those galaxies have never been directly observed. They're too faint, too small, and too distant for any telescope ever built, including Hubble, including even the James Webb Space Telescope, to see them individually. They exist, but they're invisible to us. Hidden in the noise, lost in the darkness between the galaxies we can detect. To understand how Conselius and his colleagues arrived at this number, you need to understand the approach they took, because it was fundamentally different from the method used in the deep field extrapolations. The deep field approach was essentially bottom-up. You look at a small patch of sky, count the galaxies you can see, and scale up to the full sky. The limitation of this approach is that you can only count what you can detect. You miss everything below your sensitivity threshold, and you have no direct way of knowing how much you're missing. Conselius and his team took a different approach. They started not with individual images of patches of sky, but with the accumulated data from many deep surveys taken over the previous 2 decades. They combined observations from multiple Hubble programs, including the CANDELS and GOOD surveys, which together covered larger areas of sky than any single deep field, though not as deeply as the extreme deep field. These combined datasets gave them galaxy counts across a range of distances and brightness levels. But here's the key innovation. Instead of simply extrapolating the observed counts, they analyzed how the population of galaxies changes with cosmic time. They looked at how many galaxies existed at different redshifts, which means at different epochs in the history of the universe, and they tracked how the number density of galaxies, the number of galaxies per unit volume of space, evolved from the early universe to the present day. What they found was striking. At high redshifts when the universe was young, the number density of galaxies was much higher than it is today. The early universe was packed with small galaxies. Far more small galaxies than the local universe contains now. Where did they all go? They merged. Over billions of years, small galaxies collided and combined to form larger ones. 2 small galaxies become 1 medium galaxy. Several medium galaxies merge to form a large one. This process, called hierarchical merging, is one of the fundamental mechanisms of galaxy evolution. It's how large galaxies like the Milky Way and Andromeda were built, through the gradual accumulation and absorption of smaller predecessors over cosmic time. Conselius and his team modeled this merger history mathematically. They calculated the merger rate at different epochs, estimated how many galaxies were consumed by mergers over the history of the universe, and worked backward to determine how many galaxies must have existed at each point in time to produce the population we see today. The result was the total number of galaxies in the observable universe, integrated across all epochs and accounting for those too faint to detect directly, was approximately 2 trillion. And the critical insight was this. Most of those 2 trillion galaxies are not the large, bright spirals and ellipticals that dominate our images of the cosmos. Most of them are small, very small. They are low-mass dwarf galaxies containing perhaps a few million to a few 100 million stars. In cosmic terms, these are tiny objects. The Milky Way contains somewhere between 100 billion and 400 billion stars. A typical dwarf galaxy among these hidden populations might contain 100 million or fewer. That's less than 0.1% of the Milky Way's stellar population. These small galaxies are intrinsically faint. They don't produce much light relative to the enormous distances across which we're trying to observe them. And because they're faint, they fall below the detection limits of our surveys. They're there, but we can't see them individually. We can only infer their existence statistically by analyzing how galaxy populations evolve and calculating how many small galaxies must have existed to produce the merger history we observe. Let me put this in concrete terms so you can really grasp what this means. Of the roughly 2 trillion galaxies that Consel IS and his team estimated to exist in the observable universe, only about 10%, roughly 200 billion, are bright enough and large enough for our current telescopes to detect directly. The other 90% are below the detection threshold. They're too faint, too small, too diffuse. They exist in vast numbers, scattered throughout the observable universe, but they've never appeared in any image taken by any telescope on Earth or in space. 90% of the galaxies in the observable universe have never been seen. This is a genuinely shocking statistic. It means that everything we've observed, every deep field image, every galaxy survey, every catalogue of galaxies compiled over a century of modern astronomy, represents only about 1/10 of what's actually out there. The universe we can see is just the tip of an enormous iceberg. The vast majority of galaxies remain hidden from us, detectable only through mathematical inference rather than direct observation. Now, there are important caveats to the Consel IS estimate. Not everyone in the astronomical community agrees with the 2 trillion figure. Some researchers have argued that the analysis makes assumptions about the merger rate and the faint end slope of the galaxy luminosity function that might not be correct. The luminosity function is the mathematical description of how many galaxies exist at each brightness level. At the bright end, where we can observe directly, the luminosity function is well constrained. But at the faint end, where galaxies are too dim to detect, the function has to be extrapolated, and the shape of that extrapolation matters enormously. If the luminosity function rises steeply at the faint end, meaning there are vastly more faint galaxies than bright ones, then the total count is very high, consistent with the 2 trillion estimate or even higher. If the function flattens out at some point, meaning there's a limit to how many faint galaxies exist, then the total count is lower. Different studies have found different faint end slopes depending on the dataset used, the redshift range examined, and the statistical methods employed. The 2 trillion figure remains the most widely cited revised estimate, but it carries significant uncertainty. The true number could be somewhat lower, or it could be even higher. There's also a deeper conceptual issue that deserves attention. The 2 trillion estimate includes galaxies across all cosmic epochs, visible within the observable universe. But many of those early small galaxies no longer exist as independent objects. They merged with other galaxies billions of years ago. If you asked how many independent galaxies exist right now, at this moment in cosmic time, the number would be lower than 2 trillion, because mergers have been reducing the total count for billions of years. The current number of galaxies in the observable universe, meaning galaxies that exist as separate entities today, is probably somewhere between a few hundred billion and roughly a trillion, depending on how you define the lower size limit. Still an enormous number. Still far more than the old estimate, but different from the total integrated count that includes galaxies that have since been absorbed. This distinction matters because it highlights how much the answer depends on the exact question you ask. How many galaxies exist right now? How many have ever existed? How many can we currently detect? How many would we detect with a perfect telescope? Each of these questions has a different answer, and the differences between them are not small. They can be factors of several or even 10. Before we move on, there is an entirely separate line of evidence for hidden galaxies that doesn't rely on statistical models or extrapolation at all. It comes from one of the most spectacular phenomena in astrophysics: gravitational lensing. Einstein's general theory of relativity predicts that massive objects bend the fabric of space-time around them. When light from a distant galaxy passes near a massive object, like a galaxy cluster sitting between us and the distant source, the light follows the curved space-time and gets bent. The cluster acts like a giant cosmic lens, magnifying and distorting the image of the background galaxy. In some cases, the magnification is enormous. A galaxy that would normally be far too faint for any telescope to detect becomes visible because the gravitational lens has amplified its light by factors of 10 or 20 or even more. These lensed galaxies appear as stretched, distorted arcs of light draped around the foreground cluster. They're some of the most visually striking objects in deep field images. Astronomers have exploited gravitational lensing to peer deeper into the universe than any telescope could reach on its own. Hubble's Frontier Fields program, conducted between 2013 and 2017, deliberately targeted 6 massive galaxy clusters, specifically because they act as gravitational lenses. By observing these clusters and the space behind them, astronomers could detect galaxies that would otherwise be completely invisible. The clusters, Abell 2744 and Max J 0416, were among the most powerful natural lenses studied. Behind these clusters, astronomers found populations as extremely faint, extremely distant galaxies, some of them among the smallest and faintest ever detected. These are precisely the kinds of objects that the Conselius estimate says should exist in large numbers. They're tiny, low-mass dwarf galaxies at high redshifts, too faint to see without the boost from gravitational magnification. The fact that these galaxies appear wherever astronomers point gravitational lenses supports the claim that the faint galaxy population is real and numerous. The lensing observations are consistent with the statistical models. They provide independent, direct evidence that there are far more galaxies below our normal detection limits than above them. Every time a gravitational lens reveals a population of ultra-faint background galaxies, it confirms that the darkness is hiding more than we can see on our own. Beyond the statistical arguments, there is a whole class of galaxies that has become increasingly important to this story. These are called ultra-diffuse galaxies, and they represent a population that traditional surveys are particularly bad at finding. An ultra-diffuse galaxy is roughly the size of the Milky Way in terms of the area it covers on the sky, but it contains far fewer stars. It has such a low surface brightness that it barely registers against the natural glow of the sky background. These galaxies are ghostly objects, spread out over enormous volumes but containing so little light that they're almost transparent. The existence of ultra-diffuse galaxies has been suspected for decades, But it wasn't until relatively recently that astronomers began finding them in significant numbers. In 2015, a team led by the astronomer Peter van Dok used a specially designed telescope called the Dragonfly Telephoto Array to search for these elusive objects. The Dragonfly Array is unusual. It consists of multiple telephoto lenses arranged together, optimized specifically for detecting extremely faint, extended structures that conventional telescopes miss. Traditional telescopes are designed to see small, bright, point-like objects very well, but they scatter light internally in ways that create a faint glow across the image, which can mask low surface brightness objects. The Dragonfly Array was engineered to minimize this scattered light, making it exceptionally good at finding things that are large and faint. Using this instrument, Van Dokkum and his team discovered dozens of ultra-diffuse galaxies in the Coma Cluster, a massive galaxy cluster about 320 million light-years away. These galaxies were enormous, some as large as the Milky Way in terms of their physical extent, but they contained only about 1% as many stars. They were so faint that previous surveys of the Coma Cluster, which had been studied for decades with some of the most powerful telescopes in the world, had completely missed them. Since then, ultra-diffuse galaxies have been found in many other environments, in galaxy clusters, in galaxy groups, and even in isolation in the field far from any cluster. They appear to be common. Some estimates suggest that ultra-diffuse galaxies could be as numerous as normal galaxies in certain environments, particularly in galaxy clusters where tidal interactions can puff up and distort existing galaxies, spreading their stars over larger volumes and lowering their surface brightness. One of the most famous and controversial ultra-diffuse galaxies is NGC 1052 DF2, discovered by Van Dokkum and colleagues in 2018. This galaxy attracted enormous attention because initial measurements suggested it contained almost no dark matter. This was extraordinary because virtually every galaxy ever studied is dominated by dark matter. Dark matter typically makes up 80 to 90% of a galaxy's total mass. A galaxy without dark matter challenged fundamental assumptions about how galaxies form and what holds them together. Subsequent studies have debated the dark matter content of this galaxy, with some researchers arguing that the initial estimate was off due to uncertainties in the distance measurement. The debate continues, but the broader point is clear. Ultra-diffuse galaxies are strange objects that don't fit neatly into our standard categories, and they're probably far more common than we realized. The implications for galaxy counts are significant. If ultra-diffuse galaxies are common throughout the universe, and if most of them are too faint for our surveys to detect, then the true number of galaxies in the observable universe could be even higher than the 2 trillion estimate. Conselius and his colleagues were primarily accounting for faint dwarf galaxies that are too small and too distant to see. But ultra-diffuse galaxies represent a different kind of hidden population. They're not necessarily small. Some are quite large. They're hidden not because they're far away or physically tiny, but because their light is spread so thin across such a large area that they disappear into the background. This is a fundamentally different detection problem, and it means there could be additional galaxies, potentially very large ones, that no current survey has found. Now let's talk about what the James Webb Space Telescope is showing us, because Webb is already changing the galaxy count story in ways that nobody fully anticipated. Webb launched on December 25th, 2021, and began science operations in mid-2022. It is the most powerful space telescope ever built. With a primary mirror, 6.5 meters across, nearly 3 times the diameter of Hubble's mirror. Its infrared sensitivity is extraordinary, allowing it to see objects that are completely invisible to Hubble. In its first years of operation, Webb has been conducting deep field observations of its own. These Webb deep fields are revealing galaxies at higher redshifts and fainter brightness levels than Hubble could ever reach. And the results have been surprising. Webb is finding more galaxies in the early universe than theoretical models predicted. At redshifts above 10, corresponding to times when the universe was less than about 500 million years old, the models said galaxies should be rare, small, and faint. They were supposed to be in the earlier stages of assembly, just beginning to pull together their first stars from primordial gas clouds. But Webb is finding galaxies at these extreme redshifts that are larger and more luminous than the models expected. Some appear to contain hundreds of millions of stars already, which shouldn't be possible in the time available. The universe at that point was so young that there simply hasn't been enough time, according to standard models, for that many stars to form. Either the models are wrong about how quickly stars can form in the early universe, or something else is happening that we don't understand. Several explanations have been proposed, and the debate is intense. One possibility is that the first generation of stars was more efficient at converting gas into stellar mass than we assumed. If star formation in the early universe was faster and more intense than in later epochs, perhaps because the gas was denser and cooler in certain conditions, then massive galaxies could assemble more quickly than standard models predict. Another possibility involves the role of supermassive black holes. Webb has found active black holes at surprisingly high redshifts, suggesting that black holes may have formed very early and grown rapidly. The energy released by these feeding black holes could have influenced star formation in their host galaxies in ways that current models don't fully capture. A third and more radical possibility is that our understanding of dark matter or early universe physics needs revision. If dark matter behaves differently than the standard model assumes, the gravitational scaffolding that galaxies form within could have been assembled earlier, allowing galaxies to grow faster. None of these explanations is settled. Each has supporters and skeptics. What is settled is that the early universe was more complex and more productive than anyone expected. Webb has revealed that galaxy formation didn't start slowly and build up gradually the way our models assumed. It started fast. Galaxies were assembling stars at remarkable rates within just a few 100 million years of the Big Bang. This has direct implications for galaxy counts. If the early universe contained more galaxies and more massive galaxies than our models predicted, then the total number of galaxies that have ever existed in the observable universe might need to be revised upward again. The 2 trillion figure from Consel IS and colleagues was based on models of galaxy evolution that may not fully capture what Webb is now showing us. The true number could be higher, but it's important to be cautious here. Webb's observations are still in their early stages. The sample sizes are small. Some of the most extreme claims about massive early galaxies may be revised as more data comes in and as astronomers refine their analyses. In some cases, what initially appeared to be a very massive, very distant galaxy turned out to be a less distant object whose redshift had been overestimated. Or it turned out to be contaminated by light from an active galactic nucleus, a supermassive black hole feeding on gas and emitting enormous amounts of radiation. which can make a galaxy appear brighter than its stars alone would suggest. Still, the overall trend is clear. Webb is revealing a more populated early universe than anyone expected, and this reinforces the central message of the 2 trillion estimate. The galaxies we can see directly are only a fraction of the galaxies that exist. The rest are hidden from us, detectable only through statistical inference or awaiting future instruments powerful enough to reveal them. Let me now step back and make sure the distinction between what is measured and what is inferred is absolutely clear, because this is essential to understanding what the galaxy count really means. What is measured directly is the number of galaxies visible in deep survey images. This number, across all surveys combined, is in the hundreds of billions. These are galaxies whose light has been captured by a detector, whose images have been recorded, and whose properties can be analysed. They are real, observed objects. What is inferred statistically is the existence of a much larger population of galaxies below the detection threshold. These galaxies have never been individually observed. No telescope has ever recorded their light. They are predicted to exist by mathematical models that describe how galaxy populations evolve over cosmic time. The models are built on solid foundations. They incorporate known physics, observed merger rates, measured luminosity functions, and the well-established cosmological framework. But they are still models. They involve assumptions and extrapolations. The inferred galaxies are not as certain as the observed ones. This doesn't mean the inferred galaxies aren't real. The evidence strongly suggests they are. The models are consistent with multiple independent lines of evidence. The galaxy merger history, the cosmic star formation rate, the properties of the cosmic infrared background, the statistics of gravitational lensing, all of these point toward a large population of faint, unresolved galaxies. But the exact number remains uncertain. 2 trillion is our best estimate. But it could be higher or lower by a significant margin. There is also a subtlety that's easy to overlook. The cosmic infrared background, a faint glow of infrared light that permeates all of space, provides indirect evidence for unresolved galaxies. This background radiation comes from all the galaxies in the universe that are too faint to detect individually. Their combined light, blended together into a diffuse glow, is detectable even though the individual sources are not. Measurements of the cosmic infrared background suggest that a significant fraction of the total light in the universe comes from galaxies below the detection limit of current surveys. This is consistent with the idea that most galaxies are invisible to us. Their individual light, too faint to pick out, but their collective glow measurable as a background haze. Let me put all of this together. The observable universe is roughly 93 billion light-years across. Within that volume, astronomers have directly observed hundreds of billions of galaxies through deep surveys and sky-wide catalogues. But the total number of galaxies, including those too faint, too small, or too diffuse to detect directly, is estimated to be roughly 2 trillion, give or take significant uncertainty. Most of these galaxies are small, low-mass dwarf galaxies that have never appeared in any image, and many galaxies that existed in the early universe have since merged into larger systems, reducing the total count over time. The number of independent galaxies that exist right now, at this moment, is probably between several hundred billion and roughly 1 trillion. And all of these numbers apply only to the observable universe, the volume of space from which light has had time to reach us since the Big Bang. Beyond the observable universe, there is almost certainly more, perhaps vastly more, perhaps infinitely more. The true total number of galaxies in the entire universe is a question that may never be answerable, because we are fundamentally limited by the speed of light and the age of the cosmos. We can only see so far, and beyond our horizon, the universe continues in ways we cannot observe and may never be able to observe. This is the strange reality of modern astronomy. We live in a universe so vast that most of it is hidden from us. Not hidden by dust or gas or distance alone, but hidden by the fundamental structure of space-time itself. The light from the farthest reaches of space hasn't had time to arrive. The faintest galaxies don't produce enough light to register on our detectors. And the most diffuse galaxies spread their light so thin that they vanish into the background noise of the cosmos. What we see when we look at the night sky is not the universe as it is. It is a tiny, biased sample of the universe, filtered through the limitations of our instruments, the finite speed of light, and the particular moment in cosmic history at which we happen to exist. The real universe, the full universe, is far richer, far more crowded, and far more complex than what any single observation can reveal. And that realization that the darkness is not empty, that the absence of light does not mean the absence of galaxies, that most of the universe's galaxies have never been seen by any human eye or any human-built machine, is one of the most profound insights of modern science. It tells us that the cosmos is deeper than it appears, that the universe has been assembling galaxies in staggering numbers for billions of years, most of them too faint and too small for us to notice, and that we are only just beginning to understand the true scale of what exists beyond the visible edge of the night sky. The question of how many galaxies exist is not a question with a clean answer. It is a question that depends on what we can detect, what we can infer, what we define as a galaxy, and how much of the universe we can access. The answer has changed before. It will change again. Future telescopes, future surveys, future theoretical insights will refine the number, push it higher or pull it lower, and reveal populations of galaxies we haven't even imagined yet. The count is not finished. It may never be finished, but every step deeper we take, every new instrument we build, every new observation we make, brings us closer to understanding just how many islands of light are scattered across the vast ocean of cosmic darkness. Everything we've discussed so far, every galaxy count, every deep field observation, every statistical estimate, applies only to the observable universe. The sphere of space, roughly 93 billion light years across from which light has had time to reach us since the Big Bang. But the observable universe is not the universe. It's just the part we can see. And this distinction between what we can observe and what actually exists is one of the most important and most misunderstood ideas in all of cosmology. Think of it this way. Imagine you're standing on the deck of a ship in the middle of the ocean. You can see to the horizon in every direction. Beyond the horizon, you can't see anything. But you know the ocean continues. You know there are waves and water beyond what your eyes can reach. The horizon is not the edge of the ocean. It's the edge of your view. The observable universe works the same way. The cosmic horizon is not a wall. It's not a barrier. It's not the edge of space. It's the edge of what we can currently see, set by the speed of light and the age of the universe. Beyond it, space almost certainly continues. There are almost certainly more galaxies out there, more stars, more planets, more of everything. We just can't see them. and we may never see them. The reason we can't see beyond the cosmic horizon comes down to one of the most fundamental facts about the universe. Light travels at a finite speed, about 300,000 kilometers per second. The universe is about 13.8 billion years old. So the maximum distance from which light could have reached us is limited by how far a photon could travel in 13.8 billion years. But there's a complication. The universe has been expanding the entire time. Space itself has been stretching. A photon that left a distant galaxy 13 billion years ago has been traveling through space that was expanding underneath it. By the time that photon reaches us, the galaxy that emitted it has been carried much farther away by the expansion. The galaxy might now be 46 billion light years from us, even though its light only traveled for 13 billion years. This is why the observable universe has a radius of about 46.5 billion light years rather than 13.8 billion. And here's the crucial part. The expansion of the universe is not just continuing, it's accelerating. In 1998, two independent teams of astronomers discovered that the expansion of the universe is speeding up over time. This was one of the most unexpected discoveries in the history of science. Everyone had assumed that the expansion was slowing down, that the gravitational pull of all the matter in the universe was gradually applying the brakes. Instead, some mysterious force, which we now call dark energy, is pushing the expansion to go faster and faster. Dark energy makes up roughly 68% of the total energy content of the universe, and we have almost no idea what it is. We know it exists because we can measure its effects. The acceleration of the expansion is real and well documented. But the underlying nature of dark energy remains one of the deepest mysteries in physics. Is it a property of empty space itself? Is it a new kind of field pervading the cosmos? Is it something to do with how gravity works on the larger scales? We don't know. What we do know is that it's there and that it's changing the future of the universe in profound ways. Because of this accelerating expansion, galaxies that are currently near the edge of the observable universe are being carried away from us faster and faster. At a certain distance, the expansion of space between us and a distant galaxy is occurring so rapidly that it effectively exceeds the speed of light. This doesn't violate Einstein's theory of relativity because nothing is moving through space faster than light. Space itself is expanding. The galaxy is sitting relatively still in its local patch of space. But the cumulative stretching of all the space between us and that galaxy adds up to an effective recession speed greater than 300,000 kilometers per second. This means that light emitted by that galaxy right now, at this moment, will never reach us. The photons will travel toward us at the speed of light, but the space between us will expand faster than the photons can cross it. Those photons will never arrive. The galaxy will slip permanently beyond our cosmic horizon, forever inaccessible to our observations. And it gets worse. Because the expansion is accelerating, the cosmic horizon is effectively shrinking over time. Galaxies that are currently near the edge of the observable universe will eventually cross the horizon and disappear. Their light will be stretched to infinitely long wavelengths, redshifted into oblivion, and they'll vanish from our sky. This process is already happening, slowly, but it will continue for billions of years into the future. Far in the future, trillions of years from now, the observable universe will have shrunk dramatically. Most of the galaxies we can see today will have been carried beyond the horizon by the accelerating expansion. Any intelligent beings alive at that distant time, looking out at the cosmos, will see only their own galaxy and whatever has merged with it. The rest of the universe will be invisible. They will have no way of knowing that the universe is filled with trillions of galaxies. From their perspective, the cosmos will appear to be a single galaxy surrounded by infinite, empty darkness. This is a haunting thought. It means that there is a window of time during which the universe reveals its true scale, and we happen to be living in that window. Billions of years from now, that window will have closed. The evidence will be gone. The galaxies will have disappeared beyond the horizon, taking their light with them. A future civilization might never know they existed. Now, what does all of this mean for the question of how many galaxies actually exist? If the observable universe contains roughly 2 trillion galaxies, and the observable universe is just a fraction of the total universe, then the total number of galaxies in the full universe is larger, potentially much larger. But how much larger depends on what lies beyond the horizon, and that's something we cannot observe. Cosmologists approach this question using the cosmological principle, the assumption that the universe, on the largest scales, is homogeneous and isotropic. Homogeneous means it looks roughly the same everywhere. Isotropic means it looks roughly the same in every direction. This isn't just an assumption. It's supported by observations. The cosmic microwave background, the faint afterglow of the Big Bang that fills all of space, is remarkably uniform. No matter which direction we look, the temperature of this radiation is the same to within about 1 part in 100,000. This tells us that the universe was extremely uniform in its early stages. And if the universe was uniform early on, it should still be roughly uniform on the larger scales today. If the cosmological principle holds, then the region of the universe beyond our horizon should look statistically similar to the region within it. The same types of galaxies, the same density of galaxies, the same large-scale structures of filaments and voids. There's no reason to think our observable patch is special. If you could somehow teleport to a point 10 billion light-years beyond our current horizon and look around, you'd see a universe that looks pretty much like the one we see from here. Same kinds of galaxies, same kinds of clusters, same cosmic web. This means that whatever the density of galaxies is within our observable universe, it's probably the same density beyond it. And the number of galaxies in the total universe is simply the density multiplied by the total volume. The problem is that we don't know the total volume. The simplest models of cosmology, the standard lambda CDM model that best fits our observations, are consistent with a universe that is either infinite in extent or so large that the observable universe is a negligible fraction of the whole. Measurements of the cosmic microwave background by satellites like WMAP and Planck have constrained the geometry of the universe. If the universe has positive curvature, like the surface of a sphere, then it's finite in volume, though it has no edge. If it's flat or negatively curved, it could be infinite. The best measurements indicate that the universe is very close to flat. Flat to within the precision of our instruments. And a perfectly flat universe in the simplest models is infinite. If the universe is infinite, then the total number of galaxies is also infinite. This is staggering to contemplate. Not 2 trillion, not 10 trillion, not any finite number at all. Infinite galaxies, infinite stars, infinite planets. The 2 trillion galaxies in our observable universe would be an infinitely small fraction of the whole. You could count every galaxy within our horizon and barely make a dent in the total. The observable universe, Vast as it is, with its 93 billion light-year diameter and its 2 trillion galaxies, would be less than a drop in an infinite ocean. But we need to be careful here. The statement that the universe might be infinite is based on our best models, but those models have limitations. The flatness we measure could be the result of the observable universe being a tiny patch on the surface of an enormously large but finite universe, just as a small patch of Earth's surface appears flat even though the Earth is a sphere. The universe could be finite, but so large that we can't detect its curvature. In that case, it would be very large, but not infinite. Maybe 1,000 times the size of the observable universe, maybe 1,000,000 times, maybe 1,000,000,000 times. We simply don't know. Some models from inflationary cosmology, the theory that the universe underwent a brief period of extraordinarily rapid expansion in the first fraction of a second after the Big Bang, suggests that the total universe could be vastly larger than the observable universe by a factor that is almost impossible to express in ordinary numbers. Some calculations suggest the total universe could be at least 10 to the power of 10 to the power of 60 times larger than the observable universe. That number is so large that writing it out in full would require more digits than there are atoms in the observable universe. In a universe that large, the number of galaxies would be correspondingly enormous. Trillions upon trillions upon trillions, a number so vast it becomes meaningless to try to state it. And then there are even more speculative ideas. Some theories in physics suggest that our universe might not be the only one. The concept of the multiverse arises in several different theoretical frameworks. In eternal inflation, the process that created our universe didn't happen just once. It's happening constantly, creating new bubble universes in an ever-expanding foam. Each bubble universe might have different physical constants, different laws of physics, different properties. Our universe, with its particular set of physical laws that happen to allow galaxies and stars and planets and life, would be just one among an infinite number of others. If the multiverse is real, then the question of how many galaxies exist takes on a completely different meaning. The answer wouldn't just be 2 trillion or even infinity within our universe. It would be infinity multiplied by infinity, an infinite number of galaxies in each of an infinite number of universes. But these ideas are highly speculative. We have no way to test them. No observation we can make will ever reveal what lies beyond the cosmic horizon, let alone in other universes. These concepts exist at the boundary between physics and philosophy, where scientific theories make predictions that are, in principle, untestable. So let's bring this back to what we can actually say with confidence. The observable universe contains roughly 2 trillion galaxies, most of them too faint to detect directly. This estimate is based on careful analysis of deep surveys, mathematical modeling of galaxy evolution, and statistical inference about populations below the detection threshold. It's the best answer we currently have, and it carries significant uncertainty. The true number could be somewhat lower or significantly higher. Beyond the observable universe, there are almost certainly more galaxies. If the cosmological principle holds, the density of galaxies beyond our horizon is similar to the density within it. The total number depends on the total volume of the universe, which we don't know. If the universe is finite but very large, the total number of galaxies is very large but finite. If the universe is infinite, the total number is infinite. What will the future bring? New telescopes and new surveys are poised to push the galaxy count further. The Vera C. Rubin Observatory in Chile, expected to begin full operations soon, will conduct the Legacy Survey of Space and Time, or LSST. This survey will image the entire southern sky repeatedly over 10 years, reaching depths comparable to some of the deepest Hubble observations, but across a much larger area. Where Hubble's deep fields cover tiny patches of sky, the Rubin Observatory will survey billions of galaxies across nearly half the sky. This will give us a far more complete census of the galaxy population, including better statistics on faint and low surface brightness galaxies that previous surveys have missed. The Nancy Grace Roman Space Telescope, planned for launch in the mid-2020s, will have a field of view 100 times larger than Hubble's, while maintaining comparable image quality. It will conduct wide-area infrared surveys that will detect galaxies too faint and too red for Hubble to see. Roman will bridge the gap between the narrow, deep pencil beam surveys of Hubble and the wide, shallower surveys of ground-based telescopes, providing galaxy counts across a much larger volume of space. The European Space Agency's Euclid mission, launched in 2023, is designed to map the geometry of the dark universe by observing billions of galaxies out to redshifts of about 2. While its primary goal is to study dark energy and dark matter, its galaxy catalogue will be enormous, providing new constraints on galaxy populations at moderate redshifts. And ground-based, extremely large telescopes, including the ELT being built in Chile with a primary mirror 39 meters across, will have the resolution to study individual faint galaxies at distances where current telescopes see only blurs. These instruments may resolve some of the galaxies that are currently below the detection threshold, turning inferred galaxies into observed ones. Each of these instruments will refine the galaxy count. They'll push the detection limit fainter, revealing more of the hidden population. They'll survey larger areas of sky, improving the statistics. They'll observe at wavelengths and depths that no previous instrument could reach. And with each advance, the number will change. Maybe it will go up. Maybe our models will be refined in ways that bring it down slightly. But the overall trajectory of the past century has been clear. Every time we build a better instrument, we find more galaxies. The universe has been consistently more populated than we expected at every stage of our exploration. But there is a limit. No telescope, no matter how powerful, will ever see beyond the cosmic horizon. The accelerating expansion of the universe guarantees that. The galaxies beyond our horizon are receding faster than their light can reach us. They are permanently hidden. And as the expansion continues to accelerate, more and more galaxies will slip beyond the horizon. Their light stretched to nothingness. Their existence erased from our observable sky. This means that the total number of galaxies in the full universe may be a question that science can never answer with certainty. We can estimate, we can model, we can extrapolate from the cosmological principle, but we can never observe. The answer lies beyond our reach, hidden behind a horizon that we cannot cross and that is slowly drawing closer. There's something profound in that limitation. For all our ingenuity, for all the extraordinary telescopes and mathematical models and centuries of careful observation, we are ultimately confined to our small patch of the cosmos. We can see 93 billion light years in every direction, which is an enormous volume containing trillions of galaxies. But beyond that, the universe continues, and we cannot follow. Let me return to the question we started with. How many galaxies actually exist in the universe? After everything we've explored, The honest answer is that it depends on what you mean. If you mean how many galaxies can we currently detect directly, the answer is in the hundreds of billions. These are the galaxies that appear in our surveys and catalogues, the ones whose light we have captured and whose images we have recorded. If you mean how many galaxies exist in the observable universe, including those too faint to detect, the best current estimate is roughly 2 trillion. This number is based on sophisticated analysis of how galaxy populations evolve, how small galaxies merge into larger ones, and how many faint galaxies must exist below our detection threshold. It is a model-dependent estimate with significant uncertainty, but it represents our best understanding. If you mean how many independent galaxies exist in the observable universe right now, at this moment in cosmic time, the answer is lower than 2 trillion, because mergers have been reducing the total count for billions of years. Probably somewhere between several hundred billion and roughly 1 trillion distinct galaxies exist today. And if you mean how many galaxies exist in the entire universe, including the parts beyond the cosmic horizon, the answer is unknown. It depends on the size and geometry of the total universe, which we cannot measure. If the universe is infinite, the number of galaxies is infinite. If it's finite but very large, the number could be hundreds of trillions or more. We may never know. What we do know is this: the universe is far more populated than it appears. The night sky, with its scattered points of light and vast stretches of apparent emptiness, is deeply misleading. The emptiness is an illusion. Behind every dark patch, in every direction, at every distance our telescopes can probe, there are galaxies, and beyond the reach of our telescopes, there are almost certainly more. The darkness between the stars is not empty. It's full of light too faint and too distant for us to see. The story of galaxy counting is really a story about the limits of human knowledge. It's a story about what happens when you try to measure something so vast that the act of measurement itself becomes the limiting factor. We are not limited by the universe's willingness to reveal itself. We are limited by our tools, by the speed of light, by the expansion of space, and by the finite age of the cosmos. The universe is not hiding from us. It's just bigger than our ability to observe. And yet, consider what we've accomplished. A century ago, we didn't even know other galaxies existed. We thought the Milky Way was everything. Then Hubble proved Andromeda was a separate galaxy, and the universe exploded in scale. We went from one galaxy to billions in a single generation. Then the deep field showed us that the darkness was full of galaxies we'd never imagined. Then statistical analysis suggested the true number was 10 times higher than anyone thought. And now new telescopes are revealing an early universe, more crowded with galaxies than our models predicted. In just 100 years, we've gone from thinking the universe contained one galaxy to estimating it contains 2 trillion. That's not just an increase in a number, it's a revolution in understanding. It's a transformation in how we see the cosmos and our place within it. Every one of those 2 trillion galaxies is a collection of stars, gas, dust, and dark matter. Each one has its own structure, its own history, its own story of formation and evolution. Many of them contain hundreds of billions of stars. Each of those stars might have planets. And on some of those planets, in some of those galaxies, conditions might be right for life. If life arose on Earth, orbiting one ordinary star in one ordinary galaxy, then there's no fundamental reason it couldn't arise elsewhere. The ingredients are the same everywhere. Hydrogen, helium, carbon, oxygen, the physics of star formation, the chemistry of complex molecules. These aren't unique to us, they're universal. And with 2 trillion galaxies, each containing billions of stars, the number of opportunities for life to arise is staggering. We don't know if life exists elsewhere. We have no evidence for it yet. But the sheer scale of the universe, the unimaginable number of galaxies and stars and planets, makes it seem unlikely that we're alone. The question is not whether life exists somewhere in those 2 trillion galaxies, but whether we'll ever be able to detect it across the vast distances that separate us. That's the final lesson of the galaxy count. The universe is immense, far larger than we see, far more populated than we imagined just a few decades ago. And it raises questions that push the boundaries of science itself. How many galaxies exist in the full universe? We don't know. How many harbor life? We don't know. How many contain civilizations looking back at us, asking the same questions? We don't know. The answers lie scattered across 2 trillion galaxies and possibly far more beyond the horizon. And we are here, on one small planet, orbiting one ordinary star, in one galaxy among trillions, asking the question. That's extraordinary. Not because we have the answer, but because we thought to ask. Because we built telescopes and trained them on the darkness. Because we refused to accept that the emptiness was real. Because we kept looking deeper and kept finding more. The universe didn't tell us how many galaxies it contained. We figured it out piece by piece, observation by observation, inference by inference. And the answer, even incomplete, even uncertain, is one of the most astonishing things human beings have ever learned. The darkness is full. The universe is vast. And we, tiny and brief as we are, have begun to count the uncountable. When you look up at the sky tonight, you'll see what humans have always seen. Stars scattered across the blackness, maybe the pale glow of the Milky Way. It looks quiet. It looks empty. But now you know what's hiding in that darkness. Trillions of galaxies, stretching in every direction, most of them invisible, many of them unimaginably distant. Some of them so faint that no instrument we've ever built can detect them. They're there. They've always been there. We just couldn't see them until we learned how to look. The count is not finished. It may never be finished. But every number we arrive at, every estimate we refine, every galaxy we discover hiding in the darkness, brings us one step closer to understanding the true scale of the universe we inhabit. And that journey from one galaxy to 2 trillion and beyond is one of the greatest stories science has ever told. Thank you for joining me tonight on this journey through the cosmos. If you found this exploration meaningful, a like or subscribe would mean the world to me. It helps me keep making these deep explorations of the universe and our place within it. And the next time someone asks you how many galaxies exist, you'll know the real answer. It's not a single number. It's a story about what we can see, what we can infer, and what remains forever hidden beyond the edge of the light. The universe is deeper than it appears, and we are only beginning to measure its depths. Good night.